In this video, we'll talk about linear approximation, what it is, and how it can be used to help solve some certain types of problems. So linear approximation, if you look at the two words, you're thinking about approximating something with a line. How can we think about this? There's two main ways to think about linear approximation. The first is using the definition of derivative. So we're talking about approximating some function here by a line that should be a good approximation of this function. So look at the definition of derivative. What do we see? Well, the definition here says that the derivative at some point a is equal to the limit as h goes to 0, f at a plus h minus f of a all over h. Now, if h is really small, then these things should be approximately equal to each other. So I would have then that if h is really small, f prime of a is basically the same thing as this actual ratio. It's not equal, but it's close. I can then rearrange it a little bit. I can multiply both sides by h and add f of a to both sides to give me that h f prime of a plus f of a is about the same as f at a plus h. And for making this look nicer, if I set x to be a plus h, then h is x minus a, and I can rewrite this as f at x is about the same as f at a plus f prime at a times x minus a. And if h is small, we're talking about x here that's close to a. F of x are normal function values, can be whatever they want. This over here is a line. And if I write this out, it's f prime of a times x. There's my mx part. My intercept would then be f of a minus f prime of a times a. But the point is, this is a line. And in some sense, it's a line that approximates the function near to a. For a second approach, we can look at the fact that the tangent line to a function is close to the graph so long as we're near the point of tangency. And this we sort of see in the picture here, right? The curve goes off like it does, but as long as I'm really close to the point of tangency, say like in this little bubble here, the graph and the function are really close together. And that's what the tangent line is sort of the best fit line to the curve. It does the best job approximating nearby the point. Now, what's the equation of the tangent line? Well, we know it has slope, f prime at a, and it has to go through the point af of a. That's what it means for that line to be tangent to the curve at that point. What's the equation here? Well, the equation is then y minus f of a equals f prime at a for the slope times x minus a. Or if I rearrange, y equals f at a plus f prime at a times x minus a. And this should look familiar. This is the same thing we got from the definition of derivative on the last part. So this thing here is super important for figuring out linear approximation. This is what I mean by linearization here. So our summary here, if f is a differentiable function at a point a, then we define the linearization of f at a to be that equation we got before from both the tangent line and from the definition of derivative. And we'll call it L of x, which is f of a plus f prime at a times x minus a. And the idea of linear approximation is that as long as I pick x close to a, L of x is about the same as f of x. What do we really mean by close here? That really depends on what you're looking at, but the point is the closer I get to a, the better approximation I get here, basically. So if I want to get a really good approximation, I better take x really close to a. But if I want to take some error in my approximation, I can take x further away. This is a couple different uses. The main one being if I want to get an idea of sort of what values a function takes on over some range, I can use this instead of the function really hard to compute. Another example is when you want to work out certain things by hand or get rough approximations of things, this can help a lot. Here's one way you can use this if you want to find a certain value. I want to approximate the value of the square root of 35.8 using linear approximation. What's the benefit of linear approximation here? Well, f of x is going to be the square root of x. That's hard to compute by hand. L of x, on the other hand, is written as f at a plus f prime of a times x minus a. I'm evaluating both f and f prime at the point a. So if a is a nice value for this function f, then I can evaluate this by hand. And then to follow up, if x is close to a, then L and f are about the same, and I get an approximation to this number. So I see here the square root of 35.8. What's a value close to 35.8 that I can easily take the square root of? Well, that's 36. So I'm going to take a here to be 36. Then I get from that f of a is just square root of 36, which is 6. F prime of x is going to be 1/2 times 1 over square root of x. 1/2 x to the minus 1/2. Plugging in 36 there, f prime at a is 1 over 12. So this means my linearization function, L of x, is equal to f of a, which is 6, plus f prime at a, which is 1/12, times x minus a, which is 36. Now, by linear approximation, f of 35.8 is about the same as L of 35.8, because 35.8 is close to 36, but this I can find directly. 6 plus 1/12, 35.8 minus 36. So it's 6 minus 0.2 over 12, which is 2 over 120, or 1 over 60. 6 minus 1 over 60 is 359 over 60. If we look at these values, 359 over 60 is 5.9833 repeating, and the square root of 35.8 is 5.98331, and so on. So we're close and we're accurate to about 4 decimal places, which is great for a by-hand calculation to figure out these values. That's the idea of linear approximation, how you can use it to find some values by hand you would not be able to do otherwise.